Okay, I always say that I'm going to end on time, and I never do. So we're probably going to end up going a little bit over. It's fine. So welcome to part 3. You guys have made it. Yay for you. Cool. So now we're going to go over Diels Alder, and I'm going to give you kind of a very quick, brief Diels Alder, because I do want to get into 14 and then do some practice problems. Alright, so Diels Alder, we have a diene reacting with a dienophile. We know what a diene is. It's any thing with 2 double bonds. And specifically to react in a Diels Alder reaction, it has to be conjugated. So it has to be 4 carbons with 2 double bonds. The diene is also the nucleophile, aka it's the thing doing the attacking. And it has to be an S-cis conformation, as drawn right here. The dienophile is going to be any double or triple bond. It is the electrophile, so it's the thing being attacked. And it doesn't matter whether we have a cis or a trans double bond. Anything can react. The only thing is, it's going to maintain its configuration. I also don't know why this is so zoomed out. I apologize. So if we had a trans double bond, we end with a trans product. If we had a cis double bond, we end with a cis product. That's the basics. And so the basics of the reaction mechanism is diene plus dienophile equals a ring. And, okay, so this is how I've been explaining it this semester, and it seems to be doing well. So we're going to go back to like elementary school where we did the greater than and less than crocodile things, or alligators, whatever, and we're going to do that. So, think of the diene as your crocodile. It wants to chomp, 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 and eat the dienophile, right? So it has to open up towards the dienophile. So we can say that this is the diene's mouth, and it's open to the dienophile. So we're going to start counting at the top of the mouth. We're going to say 1, 2, 3, 4. The dienophile is meh, it's whatever, so we're just going to say A and B. Doesn't matter which is which for this class. Alright, so number 1 always has a thing for A. They're always connected. Number 4 always has a thing for B. They're always connected. We're going to start with the double bond between 1 and 2. And it's going to use its electrons to complete this bond between 1 and A, which will force these electrons to complete the bond here between between B and 4. And then this double bond will move over here and create a double bond between 2 and 3. So we end up getting a 6-membered ring. We're always going to have a 6-membered ring in Diels Alder. That's Bear trying to make sure everyone knows he's here. Thank you, Bear. We get it. So these blue lines are the bonds we just made. We created 3 new bonds, and we have a cyclohexene ring. Ta-da! Any questions about the basics of Diels Alder so far? Okay. If not, we shall go into electron donating and withdrawing groups. So, electron donating groups are ones that donate electrons. Wow. And between the nucleophile and the electrophile, the nucleophile prefers donating groups. The reason for this is if you donate electrons, you give them to the double bonds have more density to attack with. So the more electron density you have, the more you can attack. So it's better to have electron donating groups on the diene. The dienophile, however, is going to have electron withdrawing groups, because the more you withdraw electrons, the more positive charge your dienophile gets, and the more likely it is to be attacked. And someone asked if we can do an example of retrosynthesis. Yeah, so I'm not going to spend time covering what all these things are. You can go back and watch the SI session, and I have a table, so if you want to just memorize at this point, that's fine. So just know these are donating and withdrawing groups. Dienes want donating. Dienophiles want withdrawing. I'll leave this up for like 1 second for you guys to see. Okay. And now, you click on this bad boy. And all this stuff was already done in SI, so please watch the SI session. I don't want to spend too much time on that stuff because I really want to show you guys retrosynthesis. And I want to show you the more difficult reaction examples. So, let's do one like so, where we have a pretty basic diene, right? And we're going to have this dienophile. So now we have a triple bond for a dienophile. And it's pretty much going to be the same exact thing as a double bond. We're still going to name it A and B. And for the diene, we're going to say 1, 2, 3, 4. 1 connects to A. 4 connects to B. Circle, circle, circle. Bear is losing his mind in the background. Please ignore that. Alright, so we know we made a double bond right here. We make a bond here. We make a bond here. This is the bond for our dienophile, right? We got rid of one of these 3 bonds, so we have 2 left over, and we end up with a CO2H as a substituent. So the only real difference between a double bond and a triple bond is a triple bond gives you an extra double bond at the end. So if a triple bond is your dienophile, you end up with an extra double bond in your answer. Okay. And I'll show you the example of the rings. I'm not going to redraw them, but I just want to remind you, if you start out with a ring and you do a Diels Alder reaction, you end up with a bicyclic. A 5-membered ring gives you 1 carbon in the bridgehead, like so. 2 carbons in the bridgehead indicate a 6-membered ring. So 6-membered ring, 2 carbons in the bridgehead. And I will leave this in case anyone wants to take a picture or anything or ask any questions. If not, we're going to do those wonderful retrosynthesis reactions. Okay. Alrighty. So, I'm going to be completely honest with you. These 2 are really good examples. These 2 are a little bit more difficult than you would have to do on your exam. We're going to go through all of them, and if you understand the concept behind these 2, you'll be good for your exam. So for this one, or for any retrosynthesis example, I should say, I'll zoom right in. And this is how I like to think about them, right? I know that there's going to be a double bond between carbon 2 and 3 of the diene, right? And so when I look at this, I think, okay, where is my double bond? In this example, we have 2 double bonds. So that means one of them belongs to the diene, and one of them means we had a triple bond as the dienophile. So how do we figure out which is which? Well, we are going to say this is double bond number 1, this is double bond number 2. And we're going to look at the substituents. So if we have a methyl and a methyl, we're going to be pretty confident, or first of all, in case you don't know, a methyl is an R group, and an R group is an electron donating group. And we know that the diene wants electron donating groups. So we can be pretty sure that double bond number 1 is the diene. But let's just double check. If we look at this substituent, we know that a carboxylic acid is an electron withdrawing group. And we know that our dienophile really likes electron withdrawing groups. So we're going to say that this double bond was from our dienophile, right? And now there's 2 ways you could look at this. I'm going to show you both ways. One is you could do the arrows backwards. And so we will start with double bond number 2 right here. And we're going to say that these electrons used to be here, which means that this bond doesn't exist. The electrons used to be here, which means that this bond didn't exist. Those electrons used to be here. And so it's a backwards circle. And what this indicates is that we had a double bond here, a double bond here, and we had a triple bond here. That's one way to do this. The other way that you could do this is you could just look at our ring, and I actually don't want to erase that because I want you guys to be able to see it afterwards, so I'm going to redraw it super quick. Okay, so we see this. We know that these 2 are electron donating. We know that these 2 are electron withdrawing. So we're pretty sure this is part of our diene. This is part of our dienophile, right? So if you don't want to do the circle, we can just go back and number things, right? So we know that our diene is numbered 1, 2, 3, 4. And we know that our dienophile is A and B, right? We know that in our final product of the Diels Alder, the double bond is between 2 and 3. So I know that this is 1, this is 2, this is 3, this is 4. Which would make this one A, that would make this one B. So instead of doing the arrows, we can just say, all right, we can get rid of this bond. That didn't used to be there. We can get rid of this bond. That didn't used to be there. Because we know we're going to make a bond between 1 and A and 4 and B. So in the retrosynthesis, we just get rid of the bond between 1 and A and the bond between 4 and B. And that would, again, give us our diene, 1, 2, 3, 4, plus our dienophile, A and B. So I know that was a lot, and I said a lot of words, and we went through it kind of fast. So does anyone have any questions about how in the world I got these answers? I'll give it a moment in case you're typing or anything. Okay, I got 1, I'm good. So, let's say 0 to 5. 0 is I am completely lost. And 5 is, yeah, I could do that in my sleep. Just about retrosynthesis. Let me know where you are. 3, that's solid. 4.8, solid. 4, solid. Cool, love to see it. All right, so let's do one more example. Alrighty, so the first thing I notice, we only have 1 double bond, and that automatically tells me I know that this has to be part of my diene, right? But just to make sure, let's see these substituents. We have a carbonyl and we have a carbonyl. A carbonyl is an electron withdrawing group, so we know that that's going to be connected to our dienophile. All right, so I will do the arrow steps first. I don't know what's wrong with Bear today. So we have this double bond, and we know that it goes back here. That's where it originated from. This bond breaks, and those electrons go here, which means this bond breaks, and those electrons go back here. So we end up with our diene. Our diene is pretty straightforward. It doesn't have any substituents. Cool. Our dienophile, though, we know it looks something like that, right? But if we end up with a trans product, that means that our double bond had to be trans. So I'm going to give myself some more space. And that looks like so. So this is our diene and our dienophile. And if you like the number way better, we can say this is 1, 2, 3, 4, A, B. 1, 2, 3, 4, A, B. And someone asked, so the arrows are always backwards? And then someone else said, does it matter which one you pick to go left or right? Oh, for a second I thought that second question was about the arrows. I'll answer the first one first. So the arrows, yes, when we're doing retrosynthesis, they're going to go backwards. And it makes the most sense to start with the double bond and just draw backwards. And that tells you which ones are broken. Because if this bond uses all of its electrons to go here, that means this bond doesn't exist. So it's backwards compared to the forward reaction of Diels Alder. I feel like that might have been more complicated than what I said initially, but you are right. For retrosynthesis, arrows go backwards. And then the second question was, does it matter which substituent goes left or right? And I believe you're talking about this product becoming this. No, it doesn't. As long as you know that they're going to be pointing opposite directions, you'll get the right answer. Just don't make a cis double bond, you know? Okay, cool. So this third one, I'm not going to go over this one because this one is genuinely just too annoyingly difficult and it always ends up taking a really long time. You won't get one like this on your exam. This is a more difficult one, but this is similar to something you will get on your exam. So we will cover this one. And just to make it wink, wink, nudge, nudge a little bit more similar to something you might see on an exam, I'm going to go ahead and get rid of that double bond. Okay. So, we know that now that I've made the little edit, we have 1 double bond. And so we know that means that had to be the diene, right? But just in case, let's look at some substituents. This is a substituent. This is a substituent. CO2H is a carboxylic acid. We know that those carboxylic acids are electron withdrawing groups. So we know that the dienophile is going to be somewhere over here, but we don't know where exactly, just based on this, right? And so again, I'm going to put my little reference in the corner, right? So I know that my diene is 1, 2, 3, 4. And I know that when I make my product, I'm going to have a double bond between carbon 2 and carbon 3. So based on this information, I can say that this is carbon 2, this is carbon 3, and that means this is carbon 1, this is carbon 4. We could have also done it the other way around. I don't know, this felt more right. Okay. So now, 1 always connects to A, so we say this is A. 2 always connects, 4 always connects to B, so we're going to say this is B. And I'm just going to make this a different color so it doesn't all look the same. All right, so we know that we're going to break the bond between A and 1 and 4 and B. So we end up with, I'm so awful at drawing sideways rings. Ta-da! And ta-da! Ta-da! This one was a little bit more difficult. It was big. It was oriented weird. There was a lot of stuff going on. Any questions about how I got this answer? Everyone's screaming in the background. I hope you guys can't hear that too much, or that it's not bothering you at least. How do you feel? No, you don't hear it? Sweet. Okay. Someone apparently brought another dog to my house, and so Bear is losing his marbles. Okay, so if I don't hear anything from anyone, I'm going to assume we're all good with this example, and we're all swag masters at this. Okay, someone said explain it again. Yes, I absolutely can. So, this time I'll do it in the backwards arrow method. So, I know that this double bond had to be part of the diene, right? And I know that that is the last bond to be formed, right, when we do the circle. So I'm going to start here, and I'm going to give these electrons back here, which means this bond breaks, and those electrons go here, which means this bond breaks, and these electrons go here. So we end up with a double bond here, a double bond here, and a double bond here. This is our diene, and this is our dienophile. Does that sound a little bit better? Okay. Cool. Alrighty, so let me zoom out so you may take your pictures or write down your notes or whatever you would like. And then we can move on. Okay, so I'm sure you heard that. Appa's also throwing a fit now, so everyone's throwing a fit. Okay. Chapter 14. We're almost there. Woo! We got this. Okay. So, for chapter 14, we're talking about aromaticity. So, we did most of this in SI, but there were some rules that we hadn't covered yet, so we're going to talk about that now. So, in order to be aromatic, you must be cyclic, planar, fully conjugated. What it means to be fully conjugated is all sp2 atoms. The last rule is something we called Huckel's rule, and Huckel's rule states that you need 4n plus 2 pi electrons to be aromatic. 4n plus 2 sounds stupid. And so what I'm going to tell you is just know anything with 2, 6, 10, 14, etc. electrons is going to be aromatic. Anti-aromatic is kind of cool because it has the first 3 rules: cyclic, planar, fully conjugated. The only difference is we have 4n pi electrons now. 4n is kind of stupid, so we're going to say 4, 8, 12, 16, etc. To be not aromatic, it's essentially going to break any of those rules. So if there's an sp3 carbon, if there's an odd number of electrons, which corresponds to odd number of radicals. What else? Yeah, if it's either, and if it's not planar. So something I will say about the planar rule is any ring that's smaller than 8 members, and 8 members just means like 8 atoms in the ring. Anything smaller than 8 atoms is going to be planar. Like, just assume it's planar. If it's 8 or more, then we're going to talk about whether or not it's planar and what exactly that means. So don't worry about planar unless we have 8 or more carbons. Alright, so other rules, I am much too lazy to write these all out again. So I'm just going to paste it here. Give me one moment. Much sorry. I had it copied so I could just be smooth and just paste it. Of course, it didn't work. Alright, so we hadn't covered these other rules in SI yet, but that is okay because we're going to go through them now, and it's all going to be A-okay. Screen share, start. Okay. So, sometimes we have heteroatoms in our ring, right? Again, heteroatom is any oxygen, nitrogen, boron, sulfur, things like that. So, these atoms can choose to be sp2 or they can be sp3. That might sound weird. We'll go over that in just one second. Just also note that if you have multiple heteroatoms that are all single bonded, they must all have the same hybridization. However, if you have a double bonded heteroatom, it has to be sp2 hybridized. Also note that if you have a heteroatom that's double bonded outside of the ring, it basically is the same as a carbocation. And just know that boron is always sp2. And now, what the heck did any of the stuff I say mean? Well, let's do these examples. I, again, don't know why there's a bond missing. I don't know what I did when I made these. So, if we have this ring, we know that it's cyclic. And since it's a small ring, we're going to say it's planar. And we are going to figure out whether this guy is sp2 or sp3. So whenever I do this, I like to go like this, sp2 versus sp3. So if there is an sp3 atom, it automatically has to be non-aromatic. No questions asked. However, if it's sp2, then it is fully conjugated and it donates one pair of electrons. So if it's sp2, it donates one pair of electrons. So in this case, if it's sp2, we have 1, 2, 3, 4, 5, 6 pi electrons. And does 6 pi electrons follow the aromatic rule or the anti-aromatic rule? Aromatic. Cool, I agree. So, what is more stable? Aromatic or not aromatic? Yes. Aromatic is super stable. Not aromatic is meh. It's whatever in the middle. Anti-aromatic is garbage. You do not want anti-aromatic. You want to avoid aromatic. You want to avoid anti-aromatic at all costs. Okay. So here we have to choose between aromatic and, if that would work, this would be so cool. We have to choose between aromatic and not aromatic. We are going to choose aromatic because that is more stable. So we are going to say that the nitrogen in this example is sp2 hybridized and our ring is aromatic. I know that's kind of weird. We haven't covered it in SI before. So how does that sound to you? Great, awful, in the middle. How do we feel? A 4. Okay, cool. I love it. Love to see it. So let me just highlight this to indicate that it's sp2, which means it's aromatic. Someone said 5. Ooh, I love to see it. Okay. So let's do another example. So here we have an oxygen that looks like it's wearing Mickey Mouse ears. And one thing I want to note. Oxygen has 2 lone pairs of electrons. We know that. However, it's only ever going to donate up to 2 electrons. You're never going to donate both lone pairs. So if he draws out both lone pairs for you, cross one of them out. It's just there to confuse you. If he doesn't draw any lone pairs out, draw one of them so that you know to count those electrons. Okay. So, we're going to do sp2 versus sp3. If it's sp3, we know it's automatically non-aromatic because it breaks the conjugated rule. If it's sp2, we know we have to count those electrons, right? So it becomes 2, 4, 6, 8 pi electrons. 8 pi electrons is anti-aromatic. So now, when we have to choose between anti and non-aromatic, non-aromatic is going to win. So this oxygen will be sp3 hybridized, and the ring will be non-aromatic. So do you kind of see the difference between the first one we did and the second one we did? And how the heteroatom can choose between sp2 and sp3? This tends to be really confusing for a lot of people. So if it doesn't make sense, that is A-okay. Someone said I get it. Oh, I really wish I had the plastic skull so I could say you guys are so ahead. Okay, I'm sorry. It's such a lame pun. It's not even funny. But okay, I'm so glad you guys get it. All right. So now we're going to see what happens when we have multiple heteroatoms. All right, so the rule was if we have multiple single bonded heteroatoms, they have to have the same hybridization. So, sp2 versus sp3. If they're sp3, automatically non-aromatic, no thoughts. If they're sp2, we have to count one lone pair from each oxygen. So we have in total 2, 4, 6, 8. Big yikes. 8 pi electrons, we just said, is anti-aromatic. So in this example, both oxygens are going to be sp3, and overall it will be non-aromatic. So that would be the difference here. There's always someone who asks, well, if one of the oxygens is sp2, and the other one is sp3, blah, 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 or what if one of them doesn't give the electrons? It doesn't work like that. So if it's sp2, it has to donate one lone pair. If it's sp3, it's automatically non-aromatic, and they both have to be the same. The weird thing here that we have to consider is boron. Boron is always sp2, but it has no electrons, no lone pair. So essentially, boron works like a carbocation. So it has to be sp2. So we are cyclic, we are planar, we are fully conjugated, and we have 2, 4, 6 pi electrons. So this one is aromatic. Another thing that we have to keep in mind, I said something about single bond versus double bond. If something is single bonded, or if a heteroatom, I should say, is single bonded, it can choose between sp2 and sp3, right? If it chooses sp2, it has to donate 2 electrons, or 1 lone pair, right? If a heteroatom is double bonded, it has to be sp2, and it only donates 1 electron. So I will write down double bonded heteroatom. Always sp2 and donates 1 single electron. So in this case, we are cyclic, we are planar, we are fully conjugated because we know it's sp2, and we have 1, 2, 3, 4, 5, 6 pi electrons, and we know that 6 pi electrons means aromatic. Yay! So this guy is aromatic. Sweet. We have one left. And we have two heteroatoms now, but one of them is single bonded, one of them is double bonded. So now we have to think. One of the rules I told you is, if we have two single bonded heteroatoms, both of them have to have the same conformation. If one of them is double bonded and one of them is single bonded, they do not have to have the same conformation. The double bonded one is always sp2, and it always donates one electron. But the single bonded oxygen can choose. So if it chooses sp2 versus sp3, let's see what we would get. sp3 always means non-aromatic. sp2 means 1, 2, 3, 4, 5, 6 pi electrons. Because remember, the plus sign, aka the carbocation, means it's sp2, but it is not donating any electrons. So in this case, we would get aromatic. We choose aromatic over not aromatic. So this oxygen turns out to be sp2, and it is an aromatic ring. Let me zoom out so you can see them all at once. These were a lot of rules. They are a little bit complicated. So take a moment, let it absorb into your brain, and let me know if you have any questions. Yes, you can absolutely see the rules. I don't know if you can see how hard I'm rolling my eyes at my bird, but she is so much. Okay. And I can zoom out in case anyone wants to see like the full page. I know it's going to be a little bit tiny, so I can zoom into specific parts if anyone wants, but here you go. Okay, so let me just... Alright, well that's the end of this handout. And I wanted to go over a couple of these. So I kept the answers for the ones we did in SI. I just wanted to do a couple more of these, and I wanted to talk about the planar rule. So we're going to do... don't look at the answer. She just sits there and says hello to herself over and over again. Honestly, mood. Okay. So, here we have an 8-membered ring. Whoa! It's so big. Okay. So, it is cyclic, and it is fully conjugated in both of these cases. So, what we're really worrying about is planar or non-planar. And we're kind of going to do this in the same way we did sp2 versus sp3. So if it's planar versus non-planar. So if it's not planar, it breaks the rule, so it's automatically non-aromatic in both of these cases. If it is planar in this example, it follows the rule, and so we're going to count 2, 4, 6, 8 pi electrons. 8 pi electrons is anti-aromatic. So, This guy is already really big. It already has a lot of ring strain. It does not want to stay on the plane, right? It doesn't want to be flat. But if it could be aromatic, it would be like, all right, fine. I'll have the ring strain and I'll be aromatic. I'll just be flat. But if being flat is going to make it anti-aromatic, that's a double unstable, right? We hate that. We hate everything about that. So it's going to be non-planar. It's going to bend out of the plane, and it's going to be non-aromatic. However, if it looks something like this, and it has 2, 4, 6 pi electrons, that would make it aromatic, right? And so this big bad boy is going to decide, hey, I'll have a little bit of ring strain, that's fine, but I'm going to stay planar, and I'm going to get the benefits of being aromatic. So it chooses to be planar, and it chooses to be aromatic. Oh, someone said thank you. Y'all are too cute. You're so welcome. Have a good night. Bye-bye. Okay. All right. Does this make sense? How do we feel about aromaticity? 0 to 5. What do we think? Do, 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 do. How's we thinking? Okay, so someone asked a question. It was, do you think you can post the parts to the aromatic stuff, to the answers to the aromatic stuff later? So, yeah, I'll do the answers in a cheat sheet thing. So I'll do it like that. And someone said 5. Yay! Well, they said 5, 5, 5, 5, 5, 5, 5, 5, 5. So, even better. Okay, so it has been like 3 hours, and I'm sure everyone is tired. We got through all the material. We haven't done any practice problems yet. Well, we did a bunch of practice, but we didn't do like the exam-like practice problems. So what I'm going to do is I will send you a packet of practice problems. I want you to work on them. They're composed of things that Dr. West gave me, like specifically to do with you guys, and questions that you guys already have access to. And so I'll send you that packet, work on them, and that's what we will do Monday in SI as like our exam review for SI. I'm really sad that we didn't get to do it at the review, but I don't want to hold you guys until 9 because it's already been 3 long hours. I will send an email about that because I, don't expect everyone to have watched this or to be here. And I hope to send out the cheat sheet and the practice problem packet by tomorrow afternoonish. Afternoon, early evening. So, if anyone wants to screenshot anything, let me know. If anyone has any questions, comments, or concerns, let me know. If not, I'm going to stop the recording, and I will see you guys next time. I will stay a minute just in case anyone has any questions. But I bid thee a goodbye and a good night.